Today's session is on robotics and artificial intelligence. Now, one of the very first robots ever built was built back half a century ago in the 1950s for General Motors to help them stack hot plates when they're building their cars. Now, that was the very first birth of the industrial robot. And since that point, we've developed robots to help us with almost every aspect of our lives, whether that be cleaning our own house or helping us explore Mars. Robots are there and they always will be from this point on. Now, artificial intelligence is allowing robotics to act and decide more intelligently. Now, that has so many applications, particularly in solving problems that are just too complex for us or too complex for any natural environment to be described. And so with AI, robotics and the capabilities of robotics is being even further enhanced. It is my absolute pleasure to be able to share my expertise as a robotics engineer and my passion for robotics with you in this session today. So today we're going to go through robotics and explore what a robot really is and what is AI and how is it developed to enhance robotic systems. We're then going to look at how you can start designing your robot for free at home today using free online software. And then for today's activity, we're going to be designing our very own BattleBot. Today we have over $600 worth of prizes to give away thanks to Core Electronics and Diode. So we're going to be drawing 5 winners just for the people who submit their activities for today. Now, of those 5 winners, the very first student will get one of each of these prizes, which means they'll get a 1-year Diode subscription. They'll get an Arduino beginner's kit, which is an excellent kit for anyone wanting to start robotics affordably. And they'll also win an AgTech machine vision workshop with us to learn how to develop their very own AgTech vision algorithms. Now, the remaining 4 winners will still get a ticket to that AgTech workshop. So there's some incredible prizes to win. For those who want to go for the major prize worth over $2,100, including a DJI drone, please feel free to head to our website and enter there.
Some of the most exciting AIs are robots that can move through the world with us, gathering data and taking actions. Robots can have wings to fly, fins to swim, wheels to drive, or legs to walk. And they can explore environments that humans can't even survive in. But unlike humans, who can do many different things, robots are built to perform specific tasks with different requirements for hardware and for learning.
So a robot is a machine that completes a task by sensing the environment, comprehending what decision to make, and then executing actions in the physical world. And this is what we mean by input, control system, and output. Now, because robots are built so task specific, really, depending on what the robot's objective is, will determine what inputs or outputs and even control system does it have. For example, what sensors is it using in its inputs? Is it using motors, or is it using other types of outputs like LEDs or sound? And what type of code does it have in there? What conditional logic is deciding on what to do? So there's so many ways to build robots, but commonality is that most of them will have feedback. Now, feedback's a way that a robot can actually check that it's done what it was supposed to do. So let's say a robot is moving towards a particular position. It will obviously have a sensor telling it how far that position is. Its control system will be deciding, okay, if I'm not at that position, turn the motors on. And the output is the motors. So you can imagine that if the robot system just did one cycle of this system, you wouldn't actually know whether it ended up there or not. For example, did the wheels slip and the calculations got misaligned? And so a way to know for sure is for the robot to get feedback on what it just did. So it can have another sensor value saying, actually, no, it's still further away. Okay, well, the control system turns the motors on again. And then it keeps checking that condition until eventually the feedback comes back and says, we are here, and the control system can then stop the motors. Now, there are tons of different examples of robotic uses. One is biomimicry, which means we can design robots to replicate evolutionary capabilities. This is the world's fastest robot, and as you might have guessed, it is modeled off a cheetah, which is a really interesting way to look at robotic design. Another type of robot, or robots that we can use, are assistive robots, which allow us as humans to extend our capabilities. For example, this is a Da Vinci surgical robot, and allows our surgeons to actually do more fine motor control without the shakiness of hands. Another example could be safety. These particular robots, bomb disposal robots, have been around for years, used in military applications to keep personnel safe. In this way, a person is able to disarm a bomb with absolutely no danger to themselves. And this is a key benefit of using robotics for this type of application. We also use robots to explore places that us as humans can actually never get to or have not been to. We've sent robots to the deepest, darkest oceans, and we've got robots on Mars that humans have never been to. So it allows us to explore places without having to physically be there. And lastly, robots are superb at repeatability. So when you've got a task that needs to be repeated hundreds, thousands, or even millions of times a day, a robot won't get fatigued, it won't get slack, it'll just do exactly what it's programmed to do. So things like assembling cars are extremely helpful when you have robots, because this is the way that you can make sure the car is made exactly the same every single time. And this is essentially why cars are so affordable in today's world. Now, I've got another video here that'll show you some even better examples of some really cool robots.
This is Pepper. Manufactured by SoftBank Robotics, Pepper is the world's first social humanoid robot that is able to recognize faces and basic human emotions. Pepper has been adopted by over 2,000 companies around the world. Pepper can also gather comprehensive data to enrich the customer base and generate shopper insights. This is Atlas, the world's most dynamic humanoid robot built by Boston Dynamics, a company that was previously owned by Google and now by SoftBank. With its 28 hydraulic joints, 4.9 feet of height, and 176 pounds weight, the robot can perform both impressive and terrifying acts, including navigating uneven terrain, jumping around a parkour course, and doing somersaults. All these activities demonstrate human-level agility, so the robot can be perfect for search and rescue operations and performing human tasks in environments where humans could not survive. Introducing Spot, a robot dog designed for industrial uses, such as carrying goods through a warehouse and inspecting a remote site with an unfavorable environment for human operators. It can run at 5.2 feet per second, has 360-degree cameras, and can operate in temperatures ranging from 4 to 113 degrees Fahrenheit. With its API and flexible payload interface, the robot can be easily customized for desired tasks. Spot is also manufactured by Boston Dynamics and is now being leased to eligible companies.
Now, when we want to design our very own robotic systems, it is all to do with the task that we want it to complete. But the way that you can break down this and make robotics designing to be a little bit more simple is to imagine what would we need to do if we were the robot completing this task. And I like to break it down into 3 systems. And I just want to talk you through that so that when we do our activity today, you can think a bit more like a robotic designer. So the very first system I like to talk about is the mechanical. Now I've got a picture down here to show you where this robotic system would be alike to in our own human body. So for example, anything that we have that can actually interact with the environment is what we would call a mechanical system. So things like hands, which are robotic grippers, or feet or legs, or anything that are actually interacting with the environment, we can consider a mechanical system. Now, how I like to describe that is to enable outputs is the mechanical system's task. So enable outputs, well, if you want to move somewhere, you would need legs or wheels if you're a robot. If you want to pick things up, you'd need hands or grippers. So that is one way you can think about one system of a robot. The next system is the electronic system. Now, if you're going to have these outputs, how do you activate them? And that's when you can look at, for example, it's synonymous to ourselves as humans, is we have internal organs that have muscles and blood and all the power that we need to activate our muscles. Now that in turn is how we power our mechanical or our hands or feet. So you can think about the electronic system as activating outputs. And in robots, these are batteries, wiring, maybe a driver that pumps more electricity into the motor to get it going. And then lastly, obviously, we think about ourselves and we have this processing unit right here called our brain. Now, robots need something similar. They need a way to decide what to do. And so that brain is the control of the outputs or the program that we upload into our robot. So once you can break robotic systems into these subsystems, now you can consider, specific for the task, what you'll need in each of these systems. Now that we've learnt about robotics, let's jump in and design our very own BattleBot. Now for today's activity, you might want to go to our website and download this template. This will help you in your design of your BattleBot. Now, if you don't want to do that or you've got some spare A4 paper lying around, feel free to just write these headings that you see here on your page so that you can have that same aid in your design. Now for today, you're going to need A4 paper or one of these templates, a pencil, an eraser, and feel free to use any coloring pens you want. Make your design as artistic as possible and be as creative as possible. I'm going to keep it simple just so that I can keep my template quite easy to read for others, but feel free to be as colorful as you wish. Now, the first thing I'm going to do is I'm just going to write my details in. So firstly, I'm just writing my name, grade, and postcode. And my design title, I'm going to call it Chaos. Feel free to name your BattleBot whatever you want. Maybe you leave the name to the end and then decide what it might look like. But I'm going to go with Chaos. Now, before I get into what design I want you guys to try and make, or what design even I'm going to make, I want to show you some really awesome BattleBot battles. So check these out, and while you're watching, just have a think about what design you might want to do and which one looks most effective.
This hit on a Warrior Claim minibot.
Illuminating the BattleBot skyline. Are you kidding me? One of the minibots has been sacrificed.
This is one of the most destructive hits in BattleBot's history. And despite this cheapness, it took out the most powerful drone in the tournament.
Let's see if that drone can get involved. Oh, shot it down. Takes out the drone. There it is. It takes out the drone with the ring. Are you kidding me? It actually worked. Oh, look at this. Uh-oh.
Blacksmith, that is.
This is Blacksmith. Oh, he got more spark. Hit him. Keep hitting him. Oh! It is on fire. Blacksmith is on fire. on Awayashi. He needs to line himself up perfectly.
So they're just a few examples of some BattleBots, and there are so many different types you could design. Now, we're going to look at building our BattleBot, looking at what weapons we want, what defense we want. And then we're going to break it into systems such as mechanical, electrical, and what code would be in it. So some ideas of some weapons could be a spinning blade, or a rotating disc saw, or it could be a flamethrower, or it could be a heavy hitting hammer. Or it could be a fact that you have a gripper that grabs your robot and just pushes it out of the arena. Things like that are all types of attacks or weapons. Then you want to think about defense. How are you going to defend yourself so that your robot doesn't die? So that could be things like what type of casing you have on your robot. It could be that you're a drone robot that is up in the air that can't be reached. It could be that you just try to evade the opponent. There are so many different ways you could design a BattleBot. So I'm really looking forward to seeing how creative you can be and what designs we do have submitted. So I'm going to draw mine now, and mine is just my own ideas, and I'm not even sure if it would work or be the best or not. But I'm going to sketch what I think would be a really cool robot to make. Now, I'm just going to start off sketching the frame, just to give me an idea of, the frame that I could use. Now, my weapon that I'd love to use would be a spinning blade. So I'm just kind of going to draw the supports coming out here. To maybe an axle. And a motor would sit on the end of here. And that would connect to some blades. Now, I recommend doing this in pencil first, because then you can rub it out if it doesn't look very good, or you change your ideas and have some better ideas. So this blade is going to be spinning around and attacking the opponents like that. Now, you don't have to get too technical. I think my blade looks a little bit too long. It might actually hit myself, but that doesn't matter. It's just the idea that we want to get across. So my weapon is a spinning blade. Now, I know it's very enticing to add 1,000 weapons, but you got to really think, what is my main objective, or what is my main weapon? If we have too many weapons, our design isn't going to be effective, because there's just so many things we need to make sure happen and succeed in our robot. So you might have a main weapon and maybe even a backup weapon. But for me, I'm going to put all the energy I have in my robot to be a spinning blade. So just make sure you're labeling as you're sketching as well. We want to label the weapon and all weapons and the defense mechanism. Now, my defense mechanism is, if I've got a big blade spinning around, it's got a lot of momentum, which means I probably won't be able to move very fast. So my defense isn't going to be agility or anything like that, but it's going to be a really solid, sturdy base. And that's what this is. Now, I think I'm going to make mine as a defense is a titanium base. But one really useful thing that I think would be really efficient is having rounded edges. See, when I look at those BattleBot battles, I see that most of the time, when the opponent, or when a robot gets hit, if it sticks and hits hard, it's going to have a lot of impact. But if the blade or whatever's trying to hit it just rolls off it, it just kind of skids past. So I'm going to make sure all my edges are rounded. So all this is kind of rounded, and this is rounded, and even rounded down here. Essentially, this would all be kind of rounded. Now, no one's going to hit me here because that's where my blade is, so I don't have to round that. But I've just rounded everything that I think people could potentially hit. So I'm hoping to deflect it rather than be impacted by their weapon. So that's my defense and weapon. Now, just make sure that you put in the things that are necessary for your robot as well. For example, I want to put in some small wheels here and here, and obviously at the back, which you probably wouldn't be able to see from this angle. But those wheels are going to kind of be hidden or shrouded from the outside because I don't want anyone to hit my wheels and then I become immobile. So I've got a few wheels here, and there's going to be 4 of them. And there's a lot of other things you can put the details of. You can make an artistic, you can put some art on this robot. Maybe you put your logo here. That would be really cool. Maybe I'll try and draw the integrated STEM logo, which may or may not be able to look legit. So there I put a logo on my bot, and maybe I put its name. Now you can get as creative as you want with your designs, and I highly encourage you to do so. So please feel free to pause the video and do your own sketch and do a few labels so that we know what's in our robot. So now let's break our robot into the 3 systems: mechanical, electrical, and software. Now I'm going to start with mechanical, and usually that's the easiest one to do because whatever you can physically see or whatever interacts with your environment, including your weapons, is what is in the mechanical system. So I'm just going to dot point them down. Now again, this is actually just a way of drafting a robot and getting an idea of what you should be building. A lot of times in robotics, you need a plan and you need to discretize systems. See, to make a complete system in one go, it can be kind of overwhelming. So you have to break it up into small parts like the mechanical, electrical, and software. And while you're building each one, you still have to check that they are compatible. For example, if you've got a large motor that attaches to my spinning blade, the next question is, do I have a battery big enough to power that? So that's looking at mechanical and electrical. And then you might think, well, what signal do I have to output to turn on that battery to then turn on the spinning blade? So you got to kind of design it separately, but always realize that they are interconnected. So I'm going to dot point my mechanical system now. So one thing I have is my weapon, and that is the actual mechanical part is the blade that's actually spinning around. That's a mechanical part that interacts with the environment. I also have my sense of movement, which is wheels. And also a mechanical part that you might not realize, but the frame is a mechanical part. It does interact with the environment and it holds everything together. So I also have my frame, which is a titanium, which is a titanium part. Now feel free to put as much information or as little as you want in here, as long as we've drafted something that has the mechanical components to it. Now electrical, I've got to think, well, for my blade, my wheels to work, what do I actually need? And so hopefully you thought of how you're going to power it. Now mine is going to be a large battery. Now in reality, if I was designing this, I'd want to know, well, what do I actually have to power? And so although the battery needs to power the blade, there's one component in between that process, and it's a motor. We put power into the motor, then the motor spins the blade. So make sure you also have, for your weapon, you have a large motor. Now, once you get your blade and you can figure out how heavy that is, then you can go and figure out, well, how big does my motor need to be to pull that blade around, and what type of speed do I need it to go at? So all this stuff is related, and it's just about knowing what's related as you design, so you can kind of check back and forth and make sure it all comes together in one go, but you can design it in 3 separate parts in a way. So anything else in electrical? Well, we probably have motors in the wheels. So I'm going to put movement, and they probably won't have to be that big really. So I'm just going to put small motors in wheels. Now we're onto the software or the code. So what type of code would we put in this robot? Well, we really have a controlled remotely robot. So an RC robot is what they're called. So that means that we don't need some complicated code with a lot of sensing, but there still might be sensors, and really inherently in a lot of motors there already are. For example, if we turn the motor that's spinning the blade around, we need a way to know that it's spinning very fast. Some motors come with some feedback so that when you send it a signal to, let's say, go 10,000 RPMs, which means revolutions per minute, it will actually know that it gets there because it's measuring its own speed as it goes. And that's that closed loop feedback we talked about in today's session. But I'm just going to kind of omit that and kind of treat that as that's something separate with the motor. What type of code would we need to control it? And so let's keep it simple, and you could do some AI algorithms here, and feel free to be creative, but I'm going to keep it simple, and I'm going to say that most of the code is related to the controller that I'll be controlling. So I might say from the controller, I might activate and turn on and turn off things, like for example, activate motor, which is the one in the weapon. I might turn motors 1, 2, 3, or 4 for movement. So I'd turn them on. And maybe if I wanted to have any sensors, I could put them in there, but for now I think that's enough. But you might want to have an on and an off switch, because I imagine that if you wanted to go and pick up your robot before or after the battle, you wouldn't want to dodge that spinning blade. So you might have a main power on or off toggle. So now that we've broken down our robot into systems, we can then start designing it. I just wanted to take a moment to show you just how good these BattleBots can be made, even with using simple electronics, a little bit of programming, and 3D printing. So these have been put on Thingiverse, and people have actually made these BattleBots. And you can see there's such a different range of BattleBots that have been made. So we're going to jump into Tinkercad now, and we're going to design our very own robot. Now, just learning how to 3D design and build electronics and then do a bit of programming is all you need to do to start robotics. We've got one here we call the Spy Gadget Robot, and I want to show you exactly how we made it so you can also make robots at home for yourself. You can see we've used 3D printing for the shell. We've used some electronics here that you can see with LEDs and some resistors and buzzers, and even an ultrasonic sensor that will detect distance. And on the back, we've got an Arduino, which is what you can program to make all this happen in a robotic system. Now, I just want to quickly show you what it does. So it's called our Spy Gadget Robot because if anything tries to creep up on it, let's say my hand tries to creep up on it, it'll actually alert anyone in a nearby distance that it is having something come up to it. And so that ultrasound has little sound waves that are hitting my hand, reflecting, going back, and then those inputs from that sensor are going back to the control system and then outputting the LEDs and the buzzer. So on the back, we have the programmable board we call an Arduino. And I highly recommend anyone starting robotics get into Arduino. They are so cheap and they are quite easy to learn. So now let's show you exactly how we built this robot. Whilst we teach all this stuff in our programs, I just want to run you through really quickly to show you how you can design robots for free online and actually simulate everything will work at home. So firstly, we have our mechanical system. Now, it's important to note that whilst we did design this and 3D printed, we did start the design first on paper. So you can see, for example, here was one of our very first sketches of this spy gadget, and also here. And we had all those dimensions already ready to go before we jumped into Tinkercad and then designed this. Now, Tinkercad is really useful because you can also assemble it and make sure that it works. And you can see we've designed everything and looked at it, and then we've gone to 3D print. So we knew our mechanical system would work. So that is our mechanical system. Now we have the electrical system. You can see we've also done this on Tinkercad where we've wired everything up. We've put our LEDs and our buzzer and our ultrasonics and also our Arduino board all hooked up together. And we can actually simulate it to be sure that it works. Now, if I click on the ultrasonic sensor, and this is an object, if I move that object too close to the sensor, you can hear that the buzzer is buzzing. And that simulated exactly what you saw in real life. So all of our system could actually be simulated here in Tinkercad. Now, it's useful to note that with robotics, there has to be a bit of programming to make that robot work. Well, we've done the mechanical, here's the electrical system, but now I can actually show you the code behind what happens in this robotic system. And this one is quite a simple one. It uses an if and an else loop. Now, I would usually go into more detail, but to keep it concise, essentially, if the ultrasound is a certain distance reading, then we'll turn the buzzer on and we'll turn this blue LED on. Else, we will do the opposite, turn the buzzer off and put this red LED on. And you can see this is quite a simple loop, which means we don't need to make it complicated and look at how AI can make this system work. So I hope you now have an understanding and appreciation just how easy robots can be made for free online using Tinkercad. Whilst we just don't have enough time to cover artificial intelligence in its totality in this session, I do want to make note where artificial intelligence, or AI for short, adds value to a robotic system. So AI deals broadly with the goal of automating decision-making for complex tasks. Now, using our example that we've done before, when we think about programming being the brain of a human, our brain does AI automatically. I mean, there's actually a lot of AI algorithms based on the neurons that our brain fires every single decision that we make. But where it adds value is essentially it gives us a way to sift through all this data and determine what data is information, and then from that information, what decision we can do. So programming is generally a list of instructions. Very, very simple. If this, then do that, or while this happens, do that, or for this case, do that. Now, those are conditional logic loops. And whilst they are very useful for simple tasks, essentially when the task gets too complex, or there's too much data, or there's too many things to consider, or even the programmers or the humans that make these robots don't know what to do, that's when AI algorithms can add value. So I've got a clip coming up that shows you just one example of an AI algorithm allowing us to make decisions when even humans don't know the answer.
Machine learning and AI algorithms tend to be pretty sophisticated, so rather than wading into the mechanisms of how they work, we're going to focus on what the algorithms do conceptually. Let's start with a simple example, deciding if a moth is a lunar moth or an emperor moth. This decision process is called classification, and an algorithm that does it is called a classifier. Although there are techniques that can use raw data for training, like photos and sounds, many algorithms reduce the complexity of real-world objects and phenomena into what are called features. Features are values that usefully characterize the things we wish to classify. For our moth example, we're going to use two features, wingspan and mass. In order to train our machine learning classifier to make good predictions, we're going to need training data. To get that, we'd send an entomologist out into a forest to collect data for both lunar and emperor moths. These experts can recognise different moths, so they not only record the feature values, but also label that data with the actual moth species. This is called labelled data. Because we only have 2 features, it's easy to visualise this data in a scatter plot. Here I've plotted data for 100 emperor moths in red and 100 lunar moths in blue. We can see that the species make 2 groupings, but there's some overlap in the middle, so it's not entirely obvious how to best separate the two. That's what machine learning algorithms do, find optimal separations. I'm just going to eyeball it and say anything less than 45 millimeters in wingspan is likely to be an emperor moth. We can add another division that says additionally mass must be less than 0.75 in order for our guess to be emperor moth. These lines that chop up the decision space are called decision boundaries. If we look closely at our data, we can see that 86 emperor moths would correctly end up inside the emperor decision region, but 14 would end up incorrectly in lunar moth territory. On the other hand, 82 lunar moths would be correct, with 18 falling onto the wrong side. A table like this showing where a classifier gets things right or wrong is called a confusion matrix, which probably should have also been the title of the last 2 movies in the Matrix trilogy. Notice that there's no way for us to draw lines that give us 100% accuracy. If we lower our wingspan decision boundary, we misclassify more emperor moths as lunars. If we raise it, we misclassify more lunar moths. The job of machine learning algorithms at a high level is to maximize correct classifications while minimizing errors. On our training data, we get 168 moths correct and 32 moths wrong, for an average classification accuracy of 84%. Now, using these decision boundaries, if we go out into the forest and encounter an unknown moth, we can measure its features and plot it onto our decision space. This is unlabeled data. Our decision boundaries offer a guess as to what species the moth is. In this case, we'd predict it's a lunar moth. This simple approach of dividing the decision space up into boxes can be represented by what's called a decision tree, which would look like this pictorially, or could be written in code using if statements like this. A machine learning algorithm that produces decision trees needs to choose what features to divide on, and then for each of those features, what values to use for the division. Decision trees are just one basic example of a machine learning technique. There are hundreds of algorithms in computer science literature today, and more are being published all the time. A few algorithms even use many decision trees working together to make a prediction. Computer scientists smugly call those forests because they contain a lot of trees. There are also non-tree based approaches like support vector machines, which essentially slice up the decision space using arbitrary lines. And these don't have to be straight lines. They can be polynomials or some other fancy mathematical function. Like before, it's the machine learning algorithm's job to figure out the best lines to provide the most accurate decision boundaries. So far, my examples have only had 2 features, which is easy enough for a human to figure out. If we add a third feature, let's say length of antennae, then our 2D lines become 3D planes, creating decision boundaries in 3 dimensions. These planes don't have to be straight either. Plus, a truly useful classifier would contend with many different moth species. Now, I think you'd agree it's getting too complicated to figure out by hand, but even this is a very basic example, just 3 features and 5 moth species. We can still show it in this 3D scatter plot. Unfortunately, there's no good way to visualize 4 features at once, or 20 features, let alone hundreds or even thousands of features. But that's what many real-world machine learning problems face.
Now onto the prize giveaway. Now, before I start this, I just want to say a huge thank you to Diode and Core Electronics for being the major sponsors of this event and giving us such awesome prizes to give away. Now, the prizes are on offer are just listed above me, and we're going to pick 5 random people from all the people who submit for today's activities, and this will happen each day. Now, of those 5 winners, the very first drawn student will get one of everything listed here. The 4 other winners will get one of this prize here for the 4 remaining prizes of this one. Now, how do you submit? Well, it's quite simple. The first thing is follow along with today's activities and take a photo of your work. Make sure in that photo you have the details such as your name, your grade, and your postcode so we can see who's actually submitting their design for this competition. Step 2 is to share that photo with us. The easiest way to do that would be to post it in the Facebook comments below this video, or if you want to email it to us, feel free to do so. Our email address is info@integratedSTEM.com.au. If you are emailing it to us, please be sure to use the heading of the session. Now, the heading of the session is above on this slide at the very top. So just use that in the subject box of your email. Lastly, be sure that you have liked our Facebook page so that you can see the announcement of the winners. Now, if you need to find our Facebook page, you can search us using the @integratedSTEM.com.au on Facebook, and you should find us. Very lastly, be sure that you get your entries in before they close. The closing dates are here now, and then the winners will be announced the following day at 5 p.m. For the major prize giveaway, you could win over $2,100 worth of prizes. For yourself, you could win a DJI drone, as well as a 2-week 3D printing program with us. And you could win exclusively for your school, our Machine Vision Ag Tech workshop. Now, registrations do close on August 28 at 1 p.m. and the winner will be drawn on the same day at 5 p.m. So to register, simply go to this website link here. It'll probably take you less than a minute to do so. On the website, there's 2 ways you can submit your entry. All the details are on the website. If you do both, you double your chances and you get 2 entries. I hope you enjoyed learning robotics and AI with me today, and I hope you took out of this session just how easy it is to start designing robotic systems today for free at home using online tools like Tinkercad. Now, if you did enjoy this session and got some value out of it, please may I ask you to share this video or our website with friends so we can help inspire more kids in technology. For those who actually want to develop skills, particularly in robotics and anything you saw today, please get onto our websites. We have programs such as electronics and simulation, 3D printing and 3D design, and programming and automation, as well as extended technology such as AI. We teach the whole range of technology, and it's something that we are extremely passionate about. Now, otherwise, a massive thank you for tuning in, and we'll see you next time.